Okie dokie. So we are live on YouTube now. Welcome to those who are joining on Zoom as well. It's great to see all y'all. I know it's only been 2 weeks, but it feels like it's been a long time. Oops. For those joining on Zoom, if you would like to introduce yourselves, as Stephen Dow already has, you're more than welcome to. Just hop over into the chat and you can introduce yourselves and where you're from. It's our little tradition here for those of you who are new. Just make sure that when you send out that message to change the little bar that says hosts and panelists to everyone, if you want to talk to everybody and not just Chris and I. And with no further ado, we're going to jump into space. Chris and I both have space appropriate shirts today. Chris, can we see yours? Oh,
Atlantis. Because the space shuttles were used to deploy some of the great space observatories.
That's something that we are missing now without the shuttles, is we don't have a large space bus to take scopes up into space. We have to launch them. I have got a space shirt on for the first time in a million years, which is a Pioneer themed space shirt, which is also a space telescope, although not in the kind really that we're really looking at today. Today we're going to be talking about astronomy and other wavelengths, and so we're talking about things. This is already starting off as quite a difficult concept because a lot of people aren't familiar with what wavelengths are in the first place and what other wavelengths would be compared to what we normally.
We're going to cover that.
So we're going to get into that, and we're going to look at the telescopes that we use to observe those wavelengths and get into sort of why that's useful, what we're looking at, all that sort of good stuff. Chris has done a lot of prep for this one, but
well, so neither of us would be considered experts on this field, but it's a fascinating field, and what I hope to achieve today with a sprinkling of information on some of the different aspects is to encourage people to do a deeper dive, do some reading. I know Wikipedia gets a bad rap sometimes, but when it comes to science and astronomy, I find that it's fairly reliable. And, there are people who make it a point of updating things, and especially new missions, new observatories, new instruments. The teams get into Wikipedia and they update the information, and it's pretty good. I think it's pretty good. So a lot of what I've got for you today comes from there, and I'll be sharing some pages from there. And yes, there's certainly a possibility that there could be some errors sprinkled, hiding now and again. But I think generally you'll be kind of fascinated and really interested in some of the. I know I was when I read up on some things that I kind of only casually knew about. So this is kind of cool.
The other thing that you can do before we jump into much too, and this is in regards to your comment about Wikipedia, is for scientific articles in Wikipedia, the references are fantastic. Like if you just go and check the references and see if there's links there, and whether or not they look legitimate, usually they do. It's a great way to find extra resources if you're looking for more stuff.
Yeah. And what's great is that because, I could certainly recommend some astronomy textbooks, but by the time you see them, they're probably 3-4 years out of date, whereas Wikipedia would tend to be almost completely current. So that's what's nice, another aspect of it. All right, so let's share my screen here and just start with some basics. Here we go. And we'll get rid of my.
And as we go along, if anyone has questions, please do throw them in the Q&A. We'll do our best to watch the chats both on YouTube and in Zoom in case there's any other questions as well.
Yeah, so, just a refresher, everyone's heard of the electromagnetic spectrum. We're talking about essentially photons of different energy / wavelengths. And the wavelength, you can invert the concept of wavelength to frequency. So the higher the frequency, the shorter the wavelength. And this graphic kind of neatly encapsulates the concept of that. So in the middle of the graph, we've got the visible spectrum. And then in the shorter end of the wavelength and also higher energy side of things, we get into ultraviolet, X-ray, and gamma ray in increasing order of energy. And then in the other direction, we get into infrared, microwave, and radio. So Jenna and I already talked about doing a radio astronomy session one of these days. So I'm actually not going to cover microwave and radio in this, in what I've prepared, because what we're really thinking about nowadays in advance of the launch of James Webb Space Telescope is kind of the visible infrared section of the electromagnetic spectrum and what that's going to come, what that's going to give us. And a couple other things I wanted to just bring up is we've got the concept of visible wavelengths. Let's just open up the visible wavelengths.
Can I just quickly mention one thing about radio and microwave wavelengths as well, is that they can pass through our atmosphere a bit better than some of these shorter wavelengths, which means that you can build things like ground-based telescopes to look at them.
Yeah. Yeah. So I've got I'll open up an infographic here in a second, and we can talk about the differences that come into play there. Yeah. So just to put kind of everything into context, here's the visible spectrum. You may have heard the mnemonic Roy G. Biv, which stands for red, orange, yellow, green, blue, indigo, violet. So kind of reverse order in this one. And again, as I said, frequency, this one's flipped around. So now the high energy, shorter wavelength spectrum is on the left instead of the previous slide where it was on the right. But we're used to just looking in a very narrow strip of the electromagnetic spectrum. But by looking at what's happening in the universe at all these other wavelengths, we can see phenomenon that are invisible to the human eye or invisible to our optical telescopes, and reveal the movements of gases and electromagnetic fields and things like that we just can't pick up just with purely visible light. Before we get into kind of the more esoteric and space-based stuff, I thought I'd talk for a minute about the imaging that people can do with their telescopes. You could put a DSLR camera on your telescope and do color imaging if you want to, or you could actually use narrowband filters where you're extracting the sections of the spectrum in which deep sky objects like galaxies glow preferentially. And one of our favorite friends is Trevor Jones. I'm going to bring up a page that he produced. Here we go, where he talks about narrowband imaging. This is him here. He's Astro Backyard. And one of the cool things that comes in kind of later in this talk, here's an example of 3 visible bands in which gases glow and contribute dominant glowing nebulas. So there's the oxygen, triply ionized oxygen, or O3, hydrogen alpha, which is what the sun is so busy in and the solar telescopes work in. And then we have sulfur 2, which is another popular band. And you can see this graph roughly spans the visible wavelength spectrum. So from 400 to 750, and these bands are subsets inside there. And what you can do is you can take images using filters that filter only those particular bands of color, and then later combine them together to produce full color images. So you can do this monochrome imaging in different bands and then produce full color images by combining them. And a lot of people will put pictures together and make the deep sky object look as if it would look to the human eye. But there's something called the Hubble palette, based from the Hubble Space Telescope. And it actually takes the colors and does something a little bit different with them. So normally hydrogen alpha is in the red part of the spectrum, but the Hubble palette assigns it the color green. And then the oxygen and the sulfur are here as well. And what that does is it actually enhances the structures and the details inside some objects that would you normally not see. So there you can find web pages. I think he mentions down here somebody that's got a gallery of their images that they processed with the Hubble palette. And as Jenna works with the library of imagery from the robotic telescope, and you can take that data and process it, right? You can use standard processing, but you can start playing around with the palette and do different things with it. So let me open up an example here.
If you're interested in this stuff, I'll send a link to Sky News' latest competition for editing the data from our robotic telescope. They have a competition where you can try your hand at editing, and possibly win an awesome prize pack that I want, but sadly staff can't win.
So this is the Heart Nebula. It's up near Cassiopeia this time of the year. And, a long exposure photograph, fairly wide. This is a fairly large object in the sky, but, it brings up the glowing red hydrogen gas, this H2 emission in this nebula. And then there's a star cluster in the middle called Melotte 15. And so this has been processed up to resemble, and this is from Wikipedia, by the way, just to sort of resemble what it would look like if you had superhuman vision. So just enhancing the image. But if you were to do it in the Hubble palette, and I'll just open this one up, kind of give you an example. I don't know if I can actually, I can toggle between these. But you can see that different structures, different parts of the nebula are emphasized in a different way. You can really get a sense of the, almost the pillars of creation style fingers penetrating in from the edge of the cloud and that kind of thing. So that part of the point of all this is that, when we're looking at astronomical data in other wavelengths, we're not seeing it the way a human eye would see it. Of course, we have to in order to visualize it, we have to take something that's normally invisible and make it visible to our eye by assigning color to the numbers, basically.
And can I point out as well that this, like the way that when you highlight specific wavelengths or highlight little bands of light where certain elements glow, it allows you to see where those elements are, whereas normally you wouldn't be able to see. So for example, let's say in this photo, oxygen is blue. In this one, you can see where the oxygen is, but if you look in the other one where you're just looking at visible light, it just all looks the same. So this lets you kind of pick out the different elements that are in it. Yeah,
so an assignment for after the session today is to take, I know that there have been images of the Ring Nebula, which we're used to seeing this nice sort of colored ring with pastel colors, but if you start looking at it with these different palettes, then it really emphasizes where's the sulfur, where's the oxygen, where's the other elements. So yeah, and it's not just designed to make it look pretty, it's also designed to allow astronomers and astrophysicists to understand why it is the way it is and what's happening in detail. So that's really helpful. All right, so let's open up. I'd have to ignore this. Open this up. Oops. Well, I have to find a file that I had set aside for us. Now, I had a link for it, but it somehow got lost. Here we go. Oh, where'd my infographic go? Here it is.
I'd also like to add as well that this kind of stuff, this like narrow little bits of wavelengths of light, is one of the most difficult things to talk about and communicate. It's been studied by people before about how hard it is to communicate these kinds of differences in light well. So if you need further explanation or you're not getting something, let us know and we can dive a little bit more into it.
Yeah, hopefully. And this overview I'm starting with, I'll sort of wind back and do a little bit more detail in a couple of minutes here. But so again, we're looking at yet another graph of basically wavelength versus, in this case, this is something else, but we've got the electromagnetic spectrum stretched out across the top here. There's the little visible strip band in the middle. You've got your radio off to the left, and then you've got your ultraviolet, X-ray, and gamma rays, higher energy range to the right. And across the bottom here, I'm not sure if it's coming through really well, but you can see here there's a graph, and this is a graph of ionospheric or atmospheric absorption. And as Jenna mentioned earlier, not all of these wavelengths reach the ground where our telescopes or sensors could view them. A number of them get absorbed by atoms and elements in our atmosphere and scattered and things like that and absorbed so that we just can't sit on the ground and see them. In order to see them or measure them, we have to get above the atmosphere or at least above most of it. And so you can see here that in the radio, so when it's gray, it means it's it's opaque. It can't get through the air. But when it's a light blue color, it means it can. And there's a graph of intensity of amount. So you can see that the radio waves here on the left easily penetrate the Earth's atmosphere. And so we can make these great big ground-based radio telescopes to peer into the universe. But when we get into the kind of infrared section of the graph, the infrared light is actually absorbed hungrily by the water vapor and the carbon dioxide. And that's exactly what global warming is all about. It's because those molecules, H2O and CO2, love grabbing the energy from the infrared and trapping it. And that's would then produce the warming inside the atmosphere. Then we get into the visible range. We've got transparent skies, so the light can come through. But as soon as we start getting into the X-ray, ultraviolet, and gamma ray, then we get absorption basically by ionizing various atoms in our atmosphere that absorb that energy and stop it from reaching the ground surface. Of course, there are exceptions. There are extremely energetic cosmic rays and things like that that can, to some degree, get through, but the majority of it is stopped by our atmosphere. So that's why we have to invent telescopes or other means of taking our instruments higher in the sky to get above the water vapor, get above the atoms and so on. So let's see, what else can we talk about?
The atmosphere, I'd like to also shout out to the atmosphere because X-rays, gamma rays, those really high energy UV rays, they're very dangerous for us. So thank you, atmosphere, for protecting us from those.
Yeah, and as we know, we are subject to a little bit of ultraviolet damage to our skins and eyes. So, there's a degree. It's not all or nothing. It's sort of a degree. All right, so let's talk about, and of course, in terms of looking at different wavelengths and different multi-wavelength astronomy, the sun is almost a completely different topic unto itself. The sun is visible in all kinds of, radiates in all kinds of different wavelengths. You just open up this astronomy picture of the day showing an example of that. Oh, wow. So we got your visible light. And then we have instruments in orbits. Many different countries have satellites in orbit that are designed to be monitoring space weather, which is the activity of the sun and the interaction of the sun's fields and plasma with Earth's system. And so you can see each wedge of this pie would represent a different wavelength of light. So, I'll touch on this a little bit more, but basically, solar science is much more than we have time for today.
Yeah.
All right, so let's start. Let's see, I wanted to talk about gamma rays first. So gamma rays are represented by very, very highly energetic photons. In fact, they're so energetic that they're really only produced at those energies by the nucleus of the atom. So they're the various atomic processes that happen in the nucleus of an atom. So the amount of energy that enter in gamma rays range from about 100 kilo electron volts or 1,000 electron volts up to beyond. So extremely high energies. They were discovered around 1900. Let me just put this one away and go back to my diagram of my infographic here. Here we go. We're talking gamma rays up in this range here, up to a tera electron volt. These are the kinds of energies that we produce in, particle accelerators, CERN, places like that. We can start to emulate some of the natural processes that the universe can throw at us. But yeah, they were first picked up around 1900 by a scientist named Paul Villard. And they were actually kind of formalized by Ernest Rutherford, who was noticing them affecting atomic nuclei. So regular gamma rays produce energies up to about 8 million electron volts, which is sort of in this range here. But the energy from quasars and kind of very active black holes, distant black holes, they're the ones that can produce through very violent processes up to a tera electron volt, or even 1,000 tera electron volt. And solar flares are also very energetic. So there's about a 511 kilo keV background. So that's sort of around in here, background to the sky. That's sort of the cosmic ray, cosmic rays sort of percolating through everything in the universe. Generally high speed electrons or photons. And as they collide with ordinary matter, they produce these sort of high energy bursts. In pulsars and stellar mass black holes, so degenerate matter, we talked a little bit about some of that in our previous session. So you can get gamma rays that are on the order of tens of million electron volts. So that's kind of in this range here. And that's from different sorts of properties. So there's an effect called Bremsstrahlung radiation, which is the energy released when you decelerate a particle. Hits another one and decelerates and gives up its kinetic energy as a gamma ray. So those are kind of relativistic speed motions when cosmic ray electrons interact with regular matter, give off this radiation. Magnetars, which are kind of spinning neutron stars, that kind of thing. They can be producing these gamma rays, but because of the intense magnetic fields around the magnetar, you end up with a pair of beams that are emanating from the axis of rotation of the magnetar. And if the geometry is right, then we get these beams sweeping past the Earth's detectors. So we can see magnetar gamma ray components to magnetars. Quasars themselves, quasars was kind of a term that was used when I was sort of coming through school. We now think of them more as kind of active supermassive black holes in the center of galaxies, that kind of thing. They're sort of consuming a lot of matter. There's a lot of material being accreted onto the around the event horizon of the black hole, and all of that friction and energy produces these intense radiation coming off the black hole. So the black hole accretion disks can be kind of putting out a kind of continuous gamma ray signal, but it will actually fluctuate. So you can see these signals kind of fluctuate in intensity over a period of weeks. And that's a nice clue that tells us that the size of the object that's producing it must be on the order of light weeks in diameter. So we know that it gives us kind of a size for some of these central black holes.
I learned today I learned that the quasars are black holes. I had no idea. Or they're powered by black holes. That's so cool. Cool. Huh.
Well, it was kind of, they were too small and too distant to resolve optically. So we just knew that they were producing all of this radiation. And now that we understand how black holes work and how accretion disks work and how, the black holes inside some galaxies are relatively quiescent and other ones, they're busy, consuming more matter. And that produces a more energetic output. So yeah, that's what we think they are. People may have heard of gamma ray bursts. So Canada is quite quite engaged in the study of gamma ray bursts. We have the CHIME radio telescope again. We'll talk about that another time. But it actually keeps an eye on the sky for gamma ray bursts. So gamma ray bursts last for 20 to 40 seconds of intense gamma rays sweeping through our detectors. They're the most energetic phenomenon kind of known in the universe so far. They might be a hypernova event, and essentially a hypernova event is an extreme explosion that's kind of in the process of generating a black hole and producing sort of this ultimate energy that gets sent in our direction, sweeps past us. So what do we use to look at these gamma rays? We've got different satellites, and this actual graph here is showing you the angular resolution and the range that the satellite was after. So we have the Compton. I think this should be the Compton telescope here. We have the Fermi Gamma Ray Space Telescope. That's the one that's labeled Fermi here. It's It's currently in operation. It was launched in 2008, and it's already 3 years past its original mission. And I think they're planning to end of mission that instrument next year, 2022. So how do you detect gamma rays? So this instrument actually uses metal sheets. It can actually look at a swath of sky about 20 degrees in diameter, swath of the sky. And what it has is that sheets of detectors that the gamma rays then can then kind of pass through. The angular resolution is about, depending on the wavelength of the gamma ray, between 3 arc minutes and 3 degrees. So we can only pinpoint the source to within a minimum amount, a much bigger uncertainty than we get for our optical telescopes, for example. So what has the Fermi telescope discovered in its time? And again, I'm just going to give you some highlights of the kinds of things that it's looked at. So it was able to detect pulsars. It discovered or measured or recorded some record-setting energy gamma ray bursts arising from the constellation of Carina and another one, Leo. Fermi bubbles. Let me just open up these Fermi bubbles. Can I find my Fermi bubbles? Here we go. I'll do it this way. So this is a schematic of the Milky Way. They're looking along the plane of the galaxy. And X-ray and gamma ray emissions are localized and generate these pods or bubbles of energetic particles emanating from those kind of the poles. So this is possibly an effect of the black hole in the center of our galaxy and to do with the radiation emanating from that black hole in the middle of the galaxy. So this was discovered by mapping the sky in gamma rays by using these telescopes. So they extend about 25,000 light years above the plane of the galaxy. What else? 2017, the Fermi telescope detected a gamma ray burst 6 minutes before LIGO detected a neutron star merger. So we're getting into the idea of multi-mode astronomy, where we have gravitational wave detectors liaising with the optical and other wavelength detectors. We try to understand the sequence of events and why things arrive when they do, and what we can do that way. Let's see, I've got another one here. This is going to open up. Nope, I'll do it this way. Here's another neat map. So this is an all-sky map in gamma rays. And the plane of the Milky Way is left to right in the center here. And the brightness is primarily to do with the combined energy from all the pulsars that are currently active in the plane of the galaxy. And then you get these spots, these isolated spots out of the plane of the galaxies, and those would be the quasars in other galaxies in the background. And you could take a map like this, and you could essentially tie it back to particular quasars, which in most astronomy apps would be QC something, and there'll be a number to go with it.
And just sorry, I don't know if you would know the answer to this question. Those bright spots that would be quasars, can you see them with like visible light?
Yeah, so they're visible. They're bright in visible light. And what used to happen is that we didn't have telescopes that were able to resolve them, in area or in size. So all that they knew was there was a distant bright spot in the sky, and people didn't really know what they were. In fact, because they were point-sized, point sources, that's why the name quasar, quasi-stellar object, was coined, because they were bright, they were tiny, but at the time we didn't realize that they were tiny because they were so distant, and that they were actually whole galaxies essentially. Good question.
We have a question from Stephen asking about the Fermi bubbles. Are there bubbles above and below a black hole, or are they only above?
So an object like a black hole is essentially spinning or rotating, and the energy that's able to get out of the black hole. So basically, the food comes in the disk around the equator of the black hole, if I can use that analogy, and then the energy that's emitted is coming out of the poles of the black hole. So,
okay, so then it would be above and below, well, like quote above and below the accretion disk kind of area.
At right angles to the accretion disk, yeah.
Okay.
Again, there might be complexities that modify that statement a little bit, but it generally comes down to that.
Okay.
That idea.
There's also, Wayne, I see a question from you asking about the Hubble Space Telescope. We're going to get to the Hubble Space Telescope more towards the end of the talk. So be prepared. And then we're going to talk about it a bunch in relation to the James Webb Space Telescope as well.
Yeah, so I'm finished talking about gamma rays. I'm going to switch to X-rays now, and then we'll do infrared. And by the time we get to infrared, we're heading into the range where we've got Hubble and James Webb. So
I'll also mention as well, for those who are, I typed this in the chat, there was a question about like what a gamma ray is versus an X-ray. And so I'll just mention it with my words instead as well. Since we're getting into X-rays are the things that you can see through your skin with. So you can kind of think of some of these in relation to that. Gamma rays are stronger than X-rays. X-rays you can see through the skin, but you can't see through the bone underneath your skin. Visible light, you can't see through the skin at all. You don't get to see any bones. And so there's sort of like different levels of energy and also different levels of harm that when it comes to that kind of light. So that's the reason you can see your bones with X-rays, is because they are more energetic and also slightly more damaging than the light that we would see with visible light. That's
right. Yeah. Yeah. So if somebody shines this energy on you, ultraviolet is okay for a while. Use sunscreen to block that. X-rays, you want to minimize that. And the gamma rays are so powerful that they can actually rip apart the nuclei of your atoms that you're made of. So luckily we don't run into those a lot. Yeah. But essentially it's that. And then when we get in the other direction, they get even less harmful. Infrared is still somewhat harmful. But then things like radio waves, they're pretty chill. Microwaves, also pretty okay. Yeah. It's a little unfortunate. I think there's misunderstanding among some people about the term radiation, right? People worry about, I was warming up my coffee this morning and I was thinking about the microwave and how, all it's doing is it's wiggling the water atoms in whatever's inside the microwave oven. It doesn't have enough energy to rip apart the atoms or the molecules in the coffee. So the way gamma rays are X-rays. And there's a question from Chris, which I actually am also curious about. I'm not sure if you know the answer. Why does the light scale switch from wavelength to voltage? Yeah, I'm not sure about that either. I think it's probably easier to measure the energy at some point than it is to, we don't have rulers that are small, fine enough to measure the wavelengths of those, but we can measure the energies relatively easily. So yeah, I'm not sure exactly if there's a rationale behind it. You can convert them, if you want to, but a lot of graphs that you'll see kind of mix the units like that. And you're right. You were saying, these boundaries between these wavelengths are not meant to be hard. There's a gradation. So they're actually the so-called range of X-rays overlaps a bit with the range of gamma rays. So a high energy X-ray would overlap with a low energy gamma ray. And the distinction generally is that X-rays are high energy photons that are kind of related to phenomenon to do with the electron. How electrons can absorb photons or emit photons in an atom. Whereas gamma rays tend to arise from nuclear physics as opposed to electron physics. Right. Okay. So on that note, actually, there was a comment on YouTube from John saying that U.S. Border Patrol, I think it was what it is,
have me drive through a gamma ray detection truck. And in that case, I think what they would be looking for is things like nuclear goods, I guess, right?
Yeah, because that's what radioactive decay is. It's all,
It's like,
alterations in the nucleus of an atom, an unstable nucleus of an atom, which tends to be the radioactive elements. So yeah, if you were trying to smuggle a dirty bomb or something like that, then the gamma ray detector picks that up.
Yeah.
Yeah.
Very cool. Okay.
Yeah.
That's it for questions for now. If you have more questions, throw them in the chat box or in Q&A and we'll get to them. Back to you, Chris, over to X-ray.
No problem.
No,
this is what I wanted. It's after Thanksgiving. we want to be relaxed and just sort of have fun with it. So,
and there is one more question from Yajat. I'm sorry if I'm pronouncing your name wrong. What are the lines which you are showing us? So the lines here are showing you, like the ones that are going horizontally, show you which different type of observing things. So like a detector or a telescope, what types of light it's getting. And that's what the length of it determines. So for example, if you look at the Parker Solar Probe, it's only seeing like a super tiny bit of light. But then if you look at Fermi or Maxi, it's seeing a whole bunch more of the light that's available.
Yeah, a bigger range of light. Yeah. So you're seeing, So essentially, Maxi is an acronym that has the word X-ray in it because it's designed to view the X-ray band and that kind of thing. And you're also seeing vertically, it's the angular resolution. So essentially, how small a spot in the sky can you see an object? Can you see an object? And you can see that an object that's got a small arc seconds, a fraction of an arc second, it's a very tiny pinpoint in the sky, and an object that's got 100 or 1,000 or more times an arc second is really only seeing a blob-sized patch of the sky.
Right. So it's a little bit more general in terms of what it observes, whereas those ones at the bottom would observe like really, really detailed things. And
it's a really fair question, and it's going to come up here in a minute, to ask, well, if a gamma ray is such a tiny short wavelength phenomenon, why can't you get sharp pictures from it? And it's because you can't focus X-rays, gamma rays, the way you can focus visible light with mirrors and lenses. They're just, because anything that you try to use to bounce the light and reflect it, they're just going to go straight through it.
Oh, that's tricky.
Yeah. So what you do is you use what's called glancing reflections. So instead of making a telescope where the gamma rays or the X-rays come in and they get bounced back up, they just go at the bottom. So what you do is you just kind of coax them in a curve and direct them into a central detector.
Interesting. I'd never considered that problem before. Of course they'd go right through. Yeah.
So that's why you're seeing the X-rays and the gamma ray instruments near the top of this graph, whereas the optical ones and the others are closer to the bottom. So they're higher resolution, so more accurate pictures. Yeah. Glad you asked that
today.
Yeah, glad you asked that. So X-rays, as I said, they kind of overlap a little bit with gamma rays, but essentially they're the same thing. They're photons, except the X-rays tend to be produced by electron interactions. They're discovered back in 1895. And again, it came down to playing around with, photoelectric tubes and producing, visible light, but then other wavelengths of light, and then things were picked up. X-rays tend to be absorbed by the Earth's atmosphere. So if you go down to that graph at the bottom, you can see it doesn't get through the Earth's atmosphere. And that's mainly because as the X-ray comes in, it encounters an atom of nitrogen, oxygen, the various things that are part of our atmosphere, and they get ionized or damaged by the X-ray, and the X-ray's energy is then dissipated, so it can't make it to the ground. So what we used to do to find out about X-rays is we knew about them on the ground because we discovered them in the lab first, but then we wondered, are they in the sky? Are they in the universe? So we would send up V2 rockets way back in 1949. So they'd send short flight up with a detector in it, and then it would drop back to Earth. And of course, it was only able to see the X-rays that might be coming from the sky above the rocket. It couldn't see below the Earth's horizon. So it could only really map a limited part of the sky that happened to be above the rocket. So if you were going to wait and do many, many rocket launches as this sort of sky rotated through the year, then you could start mapping the rest of the sky. So that was limited to a patch of sky above the rocket site. Then we started putting them in balloons, and so you would send a balloon up 40 kilometers, and that gets you above 99.997% of the Earth's atmosphere, and it can stay there for hours, but it still wasn't quite high enough to be able to see the lower energy X-rays. So we were getting a part of them, but not the full band. But that was really helpful because among the other things that were discovered using that technique were that there was a pulsar in the Crab Nebula with an X-ray source. That happened in 1964. And then back in the early 70s, we've told this story, I think, before on Insider's Guide, how the sounding rockets had identified a number of individual X-ray sources in the night sky, and people didn't know what was causing them, but they were curious to study them further. And one of the sources was in the neck of Cygnus the Swan. And so Tom Bolton at the university, who was with the University of Toronto, working at the David Dunlap Observatory in Richmond Hill, decided to point the big telescope at his best guess at where the X-ray source was. He discovered in that region a blue supergiant star. And when he took spectra of that star, he found out that the spectra was being blue shifted, red shifted over the course of several days. And the implication was that you had an X-ray source, you had a giant star that was being tugged around by some invisible object that has to be heavier than the blue star to do that. 2 and 2, you get a black hole. So the DDO telescope published the first confirmed black hole named Cygnus X1. And we talked about how to see the blue star in your telescope if you want to find it. So go back and watch the YouTube, and we show you where those stars are.
Go back to our old videos. Sorry, I'm describing electron volts in the comments, so I am listening, but I apologize for being quiet.
No problem. Yeah. So the concept of the how to focus, how to make an X-ray telescope comes down to this grazing incidence technique. So you use mirrors or a ceramic foil, and you just use minor deflections to kind of herd the X-rays towards your detector. So that really limits the kind of resolution. So you can't really, do super high res mapping of the sky that way. The Chandra X-ray telescope is one of the great space observatories. Let me see if I can bring up a picture of it here. Show you what it looks like. Here we go.
Yeah.
Here we go, the Chandra. So it's kind of a tube shape, so the X-rays are coming in the one direction and being coaxed down to the detectors at the bottom. And they essentially steer the telescope around the sky and point it at different things. So let's talk a little bit about that. It was launched in 1999 by the space shuttle. Not sure if it was Atlantis, but I'm not sure. It's still in operation. It's 17 years past its original plan. It uses 4 pairs of nested cylindrical paraboloidal and hyperboloidal surfaces coated with iridium and gold, which won't absorb the X-rays. I'm not sure there's a picture of the schematic of the detector here. But anyway, I invite you to go and take a look and do some further reading on that. Let's see. The diameter of the telescope, it's 65 to 123 centimeters. And the reason there's a range there is because it depends on which end of the X-ray energy spectrum that you're dealing with. It uses a highly eccentric orbit around the Earth. And what it's doing is it's spending part of its time close to the Earth inside the Van Allen radiation belts, but needs to spend time outside the Van Allen radiation belts where it can see the X-rays more clearly. And so it does this thing where it heads away from the Earth, does its measurements, comes in closer, downloads its data, and does this sort of over and over again.
And just a note for people who don't know what Van Allen belts are, they are an area around the Earth that protects us from radiation. Essentially, it's caused by the Earth's magnetic field, and so it almost catches the like charged particles that would normally cause problems for us, and is also one of the reasons that astronauts are more prone to problems with this kind of radiation than us on Earth, because the Van Allen belt protects us. It does not protect things that are way out in space.
Yes. So the angular resolution of the Chandra telescope is about half an arc second, which is pretty good. It's able to record the position of the X-ray source, the intensity of the X-ray source, and the energy level. So which part of the range it falls in. Among the discoveries accredited to the Chandra telescope, it discovered a ring surrounding the Crab pulsar. I think I've got a picture coming up later of that. Let's see. It found out that there were X-rays coming from galactic supermassive black holes, including Sagittarius A, which is the one in the center of our own galaxy. It's actually discovered that there is an intermediate mass black hole in Messier 82. So we knew that there were supermassive black holes in the galactic cores. We knew that heavy stars could turn into stellar mass black holes, but we weren't really sure what happened in between those two ranges. And the Chandra has discovered that there's an intermediate size one in M82. And there may be others. I haven't researched more fully on that. Chandra mapped out many black hole accretion disks across the sky. So it's one of the ways that we can make maps of where the black holes are in different constellations. You can actually use the X-ray flux from the black holes to measure their spin rate. So is it a slowly spinning black hole or is it a quickly spinning black hole? Chandra actually detected X-rays emitting from the poles of Jupiter. We know that Jupiter has an extremely intense magnetic field, and it's got aurora at the poles, and it's actually emitting X-rays from the poles. It's been able to actually study the relationship between dark matter and regular matter. I'm sure if one of these examples in here, but if you go into this page, you can look at some of these examples. They found some star flares, and those are just a sample of some of the things that they've done. So I'll pause there and see if anybody has any X-ray questions.
I've already asked all my X-ray questions, so okay. I don't have any questions to vamp with, unfortunately.
That's okay.
Coming in via Zoom. For those that need the visual representation of the wavelengths as well, the one that Chris brought up just now is very helpful. Sorry, can you go back to that, Chris?
Yeah.
Thank you. Because it just brings it down to like how the wavelengths line up. So it's got, this one's backwards flipped around from the one that we had a second ago, with this time the gamma rays on the left, then X-rays, then UV, then visible light, infrared, microwave, all that stuff. All right, enough vamping, no questions. I think we're going to continue. Well, no, just kidding. There's one question from Yajet. So what does the telescope thing actually detect? The telescope detects the light in that part of the spectrum there that says X-rays. So it's just that spot, and that light can indicate that something else is going on. So it's not always consistent like what it's looking for. Sometimes it finds things that you didn't expect it to find, or we find out that X-rays do other stuff that we haven't seen them do before. And so it just detects anything that produces X-rays like that. And what is a wavelength? So this is a really, that sounds like a simple question, but it's a very hard thing to communicate. So light as in the stuff that your eyes see that comes out of your phone, that comes out of a light on the wall, can be described as a wave. And some waves are super tight and packed together. Some waves are really far apart. Thank you, Chris. Yep. And so radio waves are really big, long waves. And we're talking about like waves that are, the size of your room. Yeah,
Size
they're
of
like waves
buildings
on-
even.
Size of buildings. And like Stephen said, they're like waves on water. So it's like that, except our eyes just detect it as different types of colors. And so we only see a very small portion of those types of waves. Some waves, most of the waves we don't see. Only the visible light waves are the ones that we see.
So here's here's a cool experiment that you can do. You need a chocolate bar, which is always good. Yeah. So if you have a microwave oven that has a rotating platter, you want to take that out and put a chocolate bar across the microwave. And you want it so that it's heated by the microwave oven without moving. And if you run the microwave oven for a little bit of time until the chocolate starts to melt, it'll melt in places along the chocolate bar that correspond to the wavelength of the microwaves.
So that's a visualization of the waves inside of the microwave, which is really cool.
Yeah.
And so then a further question, this is one of the reasons that both Chris and I were a little scared of this topic, which is there's a lot to break down. So what information do light waves give us? They give us all kinds, like it's hard to narrow it down because like I look at this and I can tell that it's green, I think. I'm not great at colors. I can look at this and tell that it's brown. So it gives you information about that. I can also look at this and using some other stuff, tell that it's wood. And telescopes can tell a lot of stuff from these light waves.
A good example of that is if you've ever seen the infrared detectors that they use in a room. And they're just basically measuring the heat in every spot in the room. And if the picture that's produced by the infrared detector is red, then it's a warm spot. And if it's blue, it's a cold spot. And you can look for places where your insulation's missing, or you may have a draft in your room, just by measuring a heat map, which your eyes can't see. But if we were designed to see in infrared, then we would see that all the time. You could see people are warm and the chairs are cool, the furniture is cool. So
in a 2019 to 2021 world, those little things that they use to measure the temperature of your forehead, those are infrared detectors, because infrared light helps us figure out what kind of temperature things are. Two notes from the audience, one main note from the audience, which is do not microwave chocolate without parental supervision if you are under the age of whatever is required for microwaving chocolate bars.
Yes. It's a family experiment. Please
incorporate your parents. Yeah.
Yeah.
And then one other question from Brian Parsons, which actually kind of plays back to what we talked about in the beginning, which was narrowband imaging, where you just look at very tiny specific wavelengths, which is which wavelengths are auroras producing?
So if you look at I don't have a solar spectrum handy, but basically when you ionize oxygen, you can produce a green glow. So when you pump energy into an oxygen atom, the electrons orbiting the oxygen nucleus get energized and jump to a higher orbital state. And when they relax back down, which they want to do, they give off a photon corresponding to the energy that they absorb. And that photon is green, basically green. So the green glow of aurora are from oxygen. You can also get oxygen doubly ionized and get red colors. You can also get blue from nitrogen and different elements. Basically, the air is mainly nitrogen with oxygen and less of other things. So basically the greens and the reds and the blues come from the oxygen and nitrogen atoms being energized by the energy from the sun that produces the aurora. So yeah, good question.
A note from Stephen as well that aurora are expected in Calgary tonight. So if you're in Calgary, go check. And I'm loving this because we are diving down rabbit holes here. Not rabbit holes, genuine, real questions that we need to answer. And this one I think is fascinating from Cloud. How is this high energy part of the electromagnetic spectrum, so that means like the gamma rays and the X-rays, converted into a visual representation? Is it meaningful for scientists, and is there a convention? So essentially what we're saying is, or what Cloud is asking, is that if you take a picture and it looks like my face, that gives you a certain amount of information. If you take a picture of my face in X-rays, our eyes don't see X-rays, so we can't really like see the picture in a way that it actually is in X-ray form. We have to make a detector that turns the X-ray light into light that we actually can see, which is why after you get your X-rays done, it's in black and white and it shows you something that you wouldn't be able to see with visible light, which is like your cheekbones and your teeth.
So that's why I talked about the Hubble palette. It's because we're just taking the data that comes in at different wavelengths and we're assigning different colors. We could assign it to make it look natural. We could assign it to make artificial. And we could take data which we normally can't even see at all and assign a color to it and make it visible. So yeah, if you go into this topic and do some research and start looking at astronomical objects at different wavelengths, you can come up with some amazing, really see some really, really neat pictures. In this picture here, this is a number of different galaxy clusters. And the blue is dark matter being detected. And then the violet or pink is X-ray emanations. And so astronomers are looking to see whether, there's a correlation between what the dark matter is doing and where the X-rays are being emanated. And, I guess it looks like perhaps not. So, but this is the sort of study that goes on by using the telescopes with the different wavelengths to apply them to things that we've been looking at for years, but now we see them in a new light. Let me give you another one. I think I've got the Crab Nebula here in different wavelengths. Here we go. Let's try this one. Here we go. Okay. So, whoops, that's all right. Stop blinking. So there's our Crab Nebula in visible light, which is an exploding supernova remnant. And we know that there's a degenerate object or a pulsar, a spinning neutron star in the center of this. That was the result of the collapse of the star that produced the supernova that made the Crab Nebula. And so if we look at it in different wavelengths, we can see some different parts of it. So first of all, we've got infrared radiation. So there's the hot gases are still glowing as the explosion kind of, dies out over a long time. So there's a different shape to it, different form to it. Here we've got radio, and that pulsar in the middle is a radio source. So it's red in the middle here because that's where the pulsar, the radio beacon is, but there's some other things going on. Again, we'll talk about radio another day. And then down here, we've got ultraviolet, and you can see that the higher the energy, the smaller the area of concern. So now these are all the same scale. So the ultraviolet source is only a fraction of the visible. And then we've got low energy. So this is ultraviolet. Now we've got low energy X-rays from the Chandra Space Telescope. And now we're starting to see the disk around the pulsar and the jets sticking out. And so this is amazing. Now we can take this theoretical model of a rotating pulsar and we can start to actually see it. And all we've done is we've taken the X-ray intensity in this map of the sky, and we've assigned it to different variations of the color purple. And so very, very bright is white, and then less bright is light purple, lesser than that is darker purple. So we make a visual representation of what the data is that we wouldn't see visually. And then here's extremely ultra high radiation, X-rays, is focusing us down onto that pulsar, which is buried in the core. So this is exactly the whole reason why we do this multi-wavelength astronomy, is to better understand some of these phenomena.
So we have a couple more questions. I want to spend a bunch of time talking about the James Webb Space Telescope because I am a big nerd, but we're going to get there. There's a question from Radha, which is, if gamma rays are so powerful, then why don't they penetrate the atmosphere? And I believe it's because they are absorbed by our atmosphere.
Yeah.
So it's less about the energy in that case and more about the stuff that's in the way, I think. Would that be fair to say, Chris?
Yeah. It's being that energy is being used up by them. So basically it dissipates on the first thing it encounters, which is the air above us.
Right. Okay.
So let me quickly go through the UV and infrared, and then that takes us right into X-ray. So ultraviolet astronomy. Ultraviolet astronomy. Let's go back to my ultraviolet here. Ultraviolet is right on the neighbor, right the neighbor to the visible. So when we get past violet, we get into ultraviolet. That's where that word comes from. And its wavelengths between 10 and 320 nanometers. Visible is sort of, 700 down to 400 nanometers. And this is just below that, so shorter than that. It's 320. Again, ultraviolet is mostly absorbed by the atmosphere above us. So most of the astronomy we do in that is space-based. Most of the stars in the sky that we see, they emit mostly visible and infrared radiation and much less ultraviolet. So if you make a map of the entire sky in ultraviolet, it'll be mostly dark, except for a few hot spots where the very young stars are forming and the very, very old stars are dying, and some galaxies. Also, gas and dust block UV light. So that's why if we do all sky maps in ultraviolet, which I can do here. So here's an infrared map of the sky. So I can take off the dust and make the Milky Way brighter because the infrared goes through it. I'll come back to that.
That's a question in the chat as well. Sorry, Serge, I will try to talk right into my microphone. That was a question in the chat as well, which is that doesn't infrared light travel through dust? And if yes, why can't we see more stars than the visible light? And we actually can see more stars, can't we, with the infrared light?
So yes, with the infrared light. In infrared, yes.
Yeah.
Yes.
Okay,
yeah.
Sorry, back to you.
Yeah, so just a few more things to say about it. Let's see. So basically, ultraviolet detectors are relatively easy to make, they're much easier to manage than X-rays and gamma rays. So we put them on all of our instruments, basically all of our space probes, all of our planetary probes. We've even got the Chandra on the moon has a UV detector. Hubble detects UV to a certain degree. So it's very, very common. We can use it to detect chemical compositions of whatever we're looking at. So we can look at the what elements or atoms that certain things are made of, gases and solid objects. We can discern densities and temperatures of the interstellar medium, the gas in the interstellar medium. Hot stars, white dwarf stars really shine brightly in ultraviolet, so we can see where those are. And again, the sun gives off all kinds of ultraviolet light. The main telescope that has been successfully mapping UV has been the Far Ultraviolet Spectroscopic Explorer, or FUSE. It should be in here somewhere. Not sure where FUSE is. Run by Johns Hopkins. It is in low Earth orbit, launched in 1999. And they were mapping primordial deuterium. So deuterium is a form of hydrogen. And the Canadians contributed to that mission. We actually produced a guidance sensor, and that guidance sensor is being adapted for the James Webb Space Telescope. So that experience by Canadian engineers has paid off in the James Webb. Let's see. Yeah, so we've used those UV instruments on New Horizons, on Juno around Jupiter, on the Cassini around Saturn, those things. Now, infrared astronomy, we've jumped over the visible, now we're in the longer wavelength band. So photons starting at 750 nanometers in the red part of the spectrum and all the way down to 300,000 nanometers, so longer wavelengths. They're discovered by William Herschel when he had a thermometer underneath a prism, a spectrum that was produced by shining sunlight through a prism. And the thermometer went up, even though there was no light shining on the table off the end of the prism where the infrared light was bent out to. Lots of instruments that we send up that observe invisible light also have infrared detectors on them because it's, a close cousin to visible light. And the thing is that infrared is essentially mapping heat. So you need to block your detectors from heat sources, including the sun, Earth, the electronics in the telescope itself. And so that's where we get into a lot of sophisticated techniques in the way we design these instruments and also the way we deploy them. The most famous infrared space telescope to date is the Spitzer Space Telescope, launched in 2003. It actually ran fine until its helium. It used liquid helium to cool its electronics to be able to see the infrared sources from the universe. That ran out in 2009. So then they switched over into what they called a warm mission, where they were still able to use the detectors to pick up some of the sort of cooler end of the range. And it actually ran out. They actually retired in 2020, and that was in a mission. That was in an orbit, a heliocentric orbit. So it was orbiting the sun, but it was following the Earth in Earth's orbit, and it was actually spiraling farther and farther from the Earth every year. And so it was called an Earth chasing orbit, where it's kind of following behind us like this. But because of the increased angle in that circular orbit, in order to beam its information back to Earth, they had to tip the spacecraft to point the antenna towards Earth, and that was exposing the sensors, the detectors, to more sun heat. And so eventually, it just became impractical. So they just decided to retire it in 2020. It used a Ritchie-Chrétien style optics telescope with a 0.85 meter aperture, f12 focal ratio for those interested. That space telescope detected light from hot Jupiters around other stars, so hot exoplanets. It found a protostar in a dark nebula in Cygnus. It actually did a map of our galaxy core, produced this map of our galaxy. And so this is the core of the Milky Way galaxy in infrared light. And it actually revealed that our galaxy's core is more of a bar shape than a ball shape. So that's why some of the schematics of the Milky Way got updated a few years ago to show a stubby bar in the center of our galaxy. It found brown dwarfs using microlensing, gravitational microlensing, and it confirmed the TRAPPIST-1 system. That's those seven terrestrial planets. Let's see if I can open this one out. Will it work? Here we go.
I love the TRAPPIST system.
There we go. So here's our solar system, sun in the middle. Here's the TRAPPIST system. But if you take the 7 planets of TRAPPIST, they all fit down in this little orbit, much smaller than Mercury's orbit. And to scale, that's Jupiter and its 4 Galilean moons to scale. So the TRAPPIST system is only a few times bigger. And the reason this works is because the TRAPPIST star is a dwarf star. So it's much cooler. So the planets can be much closer to it. And 3 of the planets are in the habitable zone of the star. Let's see, just to finish up.
And then we have a bunch of questions, and then I'm going to just rant for a bit about the James Webb Space Telescope.
Okay. So the next big infrared mission, other than James Webb, was called WFIRST. It's been renamed the Nancy Grace Roman Space Telescope. It's going to be produced at Lagrange 2. So let me just open up the Lagrange map, because this is also relevant to James Webb. So if you have the sun and a planet like Earth, the contour lines here are gravitational potential. You can think of these as slopes. So if you're in here, you're sloping towards the sun, so you'll fall towards the sun. If you're close to the Earth, your slope is towards Earth, so you fall towards Earth. And there are these points in between where the things balance out. So if you put an object here, it'll stay put because it's balanced between the tug of the sun and the tug of the Earth. There's also one that correspondingly sits here that would park there and not fall out of place. That's called L3. And there's L2, which is the one with the Earth in the middle. And you can see that the red arrows point would mean something would fall in, and the blue arrows mean something would fall out, and in the middle they balance. So anything put here will stay there, and that's called Lagrangian point 2. There's also 4 and 5, which are at degrees off fore and aft of the planet. And Jupiter does this. Jupiter has a bunch of asteroids that sit at L4 and L5. So this is what we're going to come back to this in a bit for James Webb. But the Nancy Grace Telescope is going to occupy this site. The reason you want to do this is because if you're parked here, the Earth is blocking the sun. So it keeps it cool. And also you're farther than you would be if you were in Earth orbit, so you're not affected by Earth's heat as well. So I'll pass it over to you, Jenna, and I'll just sort of chime in
Okay.
here and there on James Webb.
I'm doing my best to catch up with some of the questions in the chat, but Janine posted a great question, which I'm pretty sure we can't give an official answer on, about running her microwave during webinars like this. The sound from the TV occasionally cuts out, and sometimes Zoom disconnects and reconnects. And that, Janine, is exactly what I was going to say, is that I think it's probably interference. And I have, I'm wildly Googling support materials for all of this. I have something that gives an idea of it, if it's okay if I still screen sharing.
Yeah, I'll stop.
Which is, this is just two audio waves interfering with each other. And so you can see that if you have, and this isn't quite right, but if you have two waves going at opposing angles, there's like really bright spots and then really dim spots. And that means that sometimes the signal, or in this case for you, like your radio signal, microwave signal, amplifies stuff, and sometimes it destroys it. And in the times that it destroys it, that's when like one wave's going up, the other wave's going down, and they average out and meet in the middle.
Yeah, cancel out or add together.
Yeah. Okay. And one last question, which was from Radha. If you merge the images of Hubble, Spitzer, and Chandra, then can you learn more info? Basically, yes.
Exactly.
Like, yeah.
Yes.
That's exactly it. That's like, if we look at things in a whole bunch of different wavelengths, we learn a lot more about what's going on. Which is why
so the Crab Nebula was just one of dozens of examples that you can Google. If you search multi-wavelength astronomy, you'll get, and they're beautiful pictures.
Unbelievable, yeah. So one of the other things that I just wanted to mention briefly as a biologist is that the only reason like that we talk about things in visible light is because our eyes only see visible light. Like, there are animals out there that can see other wavelengths. There's some animals that can see infrared, like snakes, and there are some animals that can see UV, like birds. And in so doing, they gather more information about the world. So for example, if a crow looks at another crow, it doesn't just see a black bird, it sees all these different colors in UV, which we can't picture because it's a different wavelength. And so
now you've got me intrigued. I want to go and see the picture of the crow with the costume that we can't see. We think it's wearing black.
Exactly. Google pictures of crows in UV light, and you'll be able to see like a whole bunch.
Okay, I can't wait. Can we stop now? No.
Just turn off the whole stream. I'm going to turn off my well-lit elements of this, because if I don't, my computer is going to explode. So I'm going to talk about James Webb, which is I am so excited for this telescope. You have no idea. It's the next sort of like generation of telescopes coming along. And the reason it's the next generation of telescopes, first off, I want to compare it to Hubble, because Hubble did do some amazing work and it was incredible as it was. So I'm going to go and share my screen in small spurts here and do my best to find the images that I need. So there's the difference between the Hubble detector and the James Webb detector. The James Webb detector is huge. So by being bigger, you can catch more information. Also, by being bigger, it is a whole lot more difficult to get it to space. And so Hubble imaged in UV more than and visible, and Webb is imaging in infrared and visible. Correct, Chris? Did I get that right?
Sorry, say that one more time.
Hubble imaged in UV a little bit, right?
Yeah, so Hubble had had instrumentation that was able to pick up visible light, some infrared, and some UV. Yes. Okay.
Whereas the James Webb is pretty much only the red end of the visible light spectrum and infrared. It's got sensors for both. And with that, there was a question in the chat earlier. I'm going to turn this off for a second. There was a question in the chat earlier about using it to see like what you could see with that. And the Hubble is going to be looking at things like exoplanets, which is all well and good, but it's also looking at old stuff, like way deep into the galaxy. And the reason infrared is good for that is because that stuff is moving away from us really quickly. Yeah. And when things move away from us really quickly, their wavelength, technically, like it's producing the same wavelength of light as it had been all along, but since it's moving away, the wavelength looks stretched out.
Yeah.
So things like galaxies that we normally see in visible light look like they're in infrared light because they're moving away so fast from us.
That's right. So if there are Jenna and Chris and other rascals at the other end of the observable universe looking back towards us, our galaxy would be redshift, could be redshifted to the point of invisibility, even though it's our galaxy, stars are shining the light as they normally should, but the light would be so stretched out by the time it gets to them that it'll be gone from the visible range and now parked in the infrared range.
So it means that we're going to learn some really cool stuff about some really old things with this telescope. I'm going to shout out at this point, and I'll do it again later. For the months of November and December, leading up to the launch of the James Webb Space Telescope on December 18th, RASC is doing a lot of James Webb themed things. So if you follow us on social media, you'll see videos talking about Lagrange points and what's so cool about the telescope and all that sort of stuff. And we have a speaker night with a Canadian Space Agency scientist on November 9th, which you can is not up on our website yet, but it will be soon. So check that out at rasc.ca/online. So we're doing lots of really cool stuff. I am stoked about it. And to answer the questions from Yajat in the chat, which is about Lagrange points. So Chris mentioned the Lagrange points already. There's a really cool thing about Lagrange point 2, which is where the James Webb is going. So the Lagrange points are basically happy little satisfied spots that something can be around something like the Earth and the sun without it falling back to Earth or falling into the sun or what have you. So L1 is the one between the sun and the Earth. L2 is the same distance away from the Earth as L1, but in the opposite direction. L4 and L5 are two other points that are before and after the orbit of the Earth, and L3 is hidden away on the other side of the sun. There's a lot of fun people who think that there might be another planet hiding there because we can't see it because we had the suns in the way all the time. Anyway, the cool thing about L2 and also the really cool thing about James Webb in general. So Chris talked about this with the Spitzer Space Telescope. It had to reorient itself, right? And like point itself directly at the Earth and some other things to send information back, which messed up the sensors a little bit. Yeah.
The Spitzer, yeah.
So the James Webb is doing something different, which is it's keeping all of the communications stuff on one side of the telescope, on one side of the whole unit, and all of the telescope stuff, all of the observing on the other side. And so by being at Lagrange point 2, it can block out with a giant sheet. It can block out the moon, the sun, and the Earth, which are all of the points that would mess with its science. So it can look in this direction with no interruptions at all, never having to turn around, while sending all of its information back to Earth in the other direction. So it's very cool. It's great. Hubble could not do that. And it also avoids the way that it's set up at L2. It's actually not sitting right here. It's orbiting around that point in a little circle,
can orbit
vertically. So like Earth coming towards you, James Webb doing this along the side. And that. So
are you gonna show the deploy?
Oh yeah, I am. This is like my favorite thing ever. Can you see just the video?
Yes.
Okay, so I'm gonna play it without mute, like you won't be able to hear the music. This is at twice the speed just to get us through it. So it launches, right? And it separates from its launch vehicle, and then it spits out its solar panels. Now, normally, when you have a telescope or like a satellite or a telescope, that's it. That's all that really happens. Maybe the little antenna comes out, which you can see down here, or the thing that connects back to Earth. Can't remember the word for it right now. The little dish. There it is, the antenna. The James Webb has like 72 different things it needs to do on top of those. So it has to unfurl itself like the world's most expensive and complicated piece of origami in order to function. I'm going to try to skip through this a little bit because we only have so much time today. But it unfolds its solar. This pink thing here is the thing that protects the telescope from all of the heat and radiation from the sun, the Earth, and the moon. I'm going to have to stop sharing my screen because my laptop is making terrifying noises. But essentially what you end up seeing is this big unfurling of all sorts of different materials over a 30-day period, or rather about 14 days total, in order to get the scope to where it needs to be so it can observe, which is very exciting. Absolutely.
That's why this has all taken so long. It's because it's such a complicated ballet that we need to be certain that it's going to work and that it's going to go off without a hitch.
Mm-hmm.
Somebody asked about the lifespan of the telescope, and yes, it's not expected to last as long as Hubble because we can't service it, we can't upgrade it, we can't refuel it or any of that at the present time. That doesn't mean that maybe somebody won't invent a space tug that will get it out there, but at the moment, that's the plan.
The other kind of interesting point to that, because a lot of people, and I too was also very concerned. It was like, we're sending this so far away and we're not going to be able to fix it. We fixed Hubble multiple times. But right now, we don't have anything that can fix it.
Yeah, well, we don't assume that we'll be able to, but that doesn't rule it out completely.
Right. But even if it were closer to Earth, we don't have a shuttle program anymore.
Yeah.
We don't have anything that can fix it, even if it stayed in Earth orbit. And so, yes, Nahi-Claude, I too am very anxious about how it all unfolds. And that's why we should all be very stressed and terrified about this unfolding process, and very excited. It's just like, it's absolutely fascinating.
So those mirrors, they're made of beryllium, which is more stable than glass. So they'll keep their shape, and they're gold plated because gold reflects infrared extremely efficiently. So that's cool too.
Yeah, it's just going to be absolutely amazing. I've already told you all the stuff that I think is particularly cool about it. It's got all sorts of different sensors. There's like sensors made by Canadians, by the Canadian Space Agency on there, which means that Canadian scientists get guaranteed time on the telescope, which means that we get to do some really cool research projects. And yeah,
so the Canadians get to reinstall or upgrade their Spitzer instrument, or the one I mentioned a few minutes ago, the fine guiding. So it'll actually, that instrument will allow them to aim the telescope at a target, keep it stable, and also do guiding. So those astro imagers out there that use guiding cameras, the Canadian instrument is a guide scope for the James Webb Space Telescope, which is cool.
There's a couple of questions in the chat. How long will the James Webb take to get to L2? It's going to take a month. If all the unfurling happens in the first 14 days, and then the next 14 days is getting out to the Lagrange point 2. And then Radha says, that means the telescope costs trillions of dollars, even more than Hubble, right? Not quite trillions, but in the billions. Yeah, it costs a lot of money. And the other thing too is that, I mean, we only get one shot. I'm not going to break into Eminem lyrics here, but we really need to get it right. And it's worth putting that extra time and money in order to get it right in this case.
Yep.
Question from Jamie, and I'm not entirely sure I know the answer. How in the world, or out of this world, does guiding work on a space telescope? I assume that instead of using like little motors to move things around a little bit, it's moving gyroscopes.
No. So the optical train of the James Webb Space Telescope, it actually has 4 mirrors in the optical train. So it's got the primary mirror, the secondary mirror, the tertiary mirror, and then a little mirror that does a fine adjustment that accounts for any offsets. Let's see if I have that picture here. Let's see. I think I have it here.
That's really cool. We have a similar-ish kind of thing on our telescope in California, which is just essentially a prism that changes like once every 100th of a second or something like that, to stabilize the image as well as possible.
Yeah. So this image shows the 18 beryllium gold-plated beryllium mirrors. So you've got this is your primary mirror. Your secondary mirror is on this boom that folds down, and then the tertiary mirror is inside the hole in the middle. So here's the diagram here. Light comes in, gets focused by the primary, sent to the secondary, which is actually not flat. It's a hyperbolic mirror. That light is focused down into this tertiary mirror through a hole in the center mirror, and then it's sent into a fine steering mirror and then onto the focal plane where the instrumentation is. So the combination of these little mirrors let us do guiding and almost like, I forget the term that we use on the ground, adaptive optics.
Yeah, adaptive
almost in that
optics. That's
sense.
really cool. Huh.
Yeah.
All right, we're running out of time. I'm gonna do my best to send those links. There's one person requesting the links to the James Webb Space Telescope stuff. A lot of this stuff can just be found on the internet by searching for James Webb. Take a look at the Canadian Space Agency stuff. They have lots of information about the James Webb directly from our Canadian folks, which is always really nice. Well, there was one last question from a couple people, and I'm not entirely sure I know the answer to this. How do we detect dark matter? Because it's not, dark matter is so called because it doesn't reflect or alter electromagnetic radiation, light, which is what we're detecting in.
And normally what we're doing is we're detecting it indirectly. We're detecting it by its impact on matter we can see. So, for example, the dark matter halo around the rotating Milky Way was determined by Vera Rubin because she realized that the mass distribution in the plane of our galaxy would cause everything in the rotating galaxy to rotate at a particular speed. It wasn't doing that. And the only answer to that was that there was a dark matter halo of mass, which was invisible mass, which altered the dynamics of the rotating galaxy. And so she should have gotten more recognition for that. We're recognizing her now, yes. But yeah, she was able to look at the way the visible matter was behaving and calculate what the dark matter was doing.
So basically the answer is we can't directly see it, not yet, but
No.
we can see what it does to other stuff.
Yeah.
All right, we are at time. Hopefully that whirlwind of electromagnetic radiation was enjoyable. Thank you so much, Chris, for sharing so much of that with us. Thank you to the audience as well for asking so many great questions and helping us sort of like dive into the stuff that you care about. So we really appreciate it.
Yeah, so don't buy the X-ray glasses from the comic books and think you're going to go outside on a clear night. It doesn't work that way. Sorry.
See amazing things. Yeah, it's not a good idea. Yeah.
If only.
If only. Next time we are doing binocular astronomy. So bring your binoculars and we'll be talking about a little bit more lighthearted observing-y type stuff.
So what to see. And then we're gonna dive into the moon in a month. Yeah. And that's going to be fantastic. I've got fantastic stuff to share with you on the moon. It's going to be great.
Get excited, everybody. We'll see you in 2 weeks on October 26th. Have yourselves a wonderful couple of days and clear skies.
Clear skies. Keep looking.